Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is one MCQ. The question is, what is the major product of these reaction? This is actually paraxylene. If you treat it with HF-BF3, what is the product? So 4 options are provided. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box. I believe you have tried, so let's start. Now student, this is actually a little unique problem. Why? Because I have given a mixture HF, we know it's a halogen acid, and we have taken a BF3. So I have taken an acid and plus a Lewis acid combination. What happens? Now if I say HF as acid, then HF will produce H plus F minus. And this F minus will further react with the BF3 present, because this BF3 is actually a Lewis acid or 6 electron species. So in order to fulfill its octet, it consumes this F minus. So the conjugate base for this HF is consumed by BF3. So consequently, ultimately what it produces H plus BF4 minus. Student, this BF4 minus or tetrafluoroborate is a very unique molecule. This is actually a non-nucleophilic or non-basic anion. Very unique. So consequently, this H plus is a very strong acid, and often it is called as superacid. By the way, I have already discussed a dedicated lecture on this. Check the description box and I button. Now, so it's a very strong acid. Individually, HF is a weak acid, but this HF-BF3 combination results in a very strong acid. So these reaction will produce very strong acid or superacid. So what it does with this paraxylene? Now this H plus reacts as an electrophile and reacts with this aromatic nucleus, because this aromatic nucleus or this paraxylene is called as pi excess or pi electron rich. So instead of excess, you can say pi rich also. That is more accurate. And benzene is electron rich. By the way, there are 2 methyl group, so which also result their plus I effect. Consequently, this benzene ring is relatively more electron rich compared to simple benzene or unsubstituted benzene. So if it is more electron rich, it is more reactive towards the reaction with any electrophile here, which is H plus. So consequently, what happens? One double bond consumes this H plus. Actually, if you look at the position of this carbon or this carbon is para with respect to one another, and methyl group is ortho-para orienting. So this proton addition will happen there, and after this proton addition, it will produce this protonated species. Agree? Now here aromaticity is disturbed. So in order to gain the aromaticity back, these methyl group will come out. So what it will produce? It will produce toluene plus methyl cation. Now you can say, sir, is it really possible? Actually student, this is possible for superacids. Now we know toluene, methyl group is ortho-para orienting. So if you do ortho, then you can get these 1, 2 substituted benzene derivative or orthoxylene. If you get para, then you will get the reactant back. By the way, these two are kinetically controlled product or KCP. Okay, but since the reaction medium is very strong acidic, so ultimately reaction will try to go some more stable pathway. And in this case, it will actually end up, this methyl group will actually act as electrophile, and through aromatic electrophilic substitution, it will end up in metaxylene. Now question why? Now if I ask who is more reactive between orthoxylene, paraxylene versus metaxylene, I would say ortho and para are more reactive, because this methyl group increases the electron density in each other's place, ortho and para position. But in this case, these two methyl groups are meta to each other. That's why they will not increase electron density to a particular position. What I mean, these these. So they will not increase the electron density that much. It will delocalize more, and more the electron density, less is the stability. So consequently I can say this metaxylene is actually relatively less reactive and more stable, or you can say, sir, it is a thermodynamic control product, or TCP. So that is actually the product here. So here response, main reason, these HF-BF3 combination which results in a superacid formation. And by the way, some information I want to give, you can pause and read the whole image. Now one thing I can write, that this BF3H4 mixture is highly acidic and they can produce superacid. So you can see this I have taken from Wikipedia, fluoroboric acid, you can verify. Not only that, I have taken this problem from this source. Now here you can see, if you take orthoxylene or paraxylene both, and if you treat them with this HF and BF3 mixture, they ultimately end up with this meta isomer which I called as TCP, thermodynamic control product, or most stable product. And by the way, these kinetic things, the ortho and para isomers, are relatively more electron rich, that's why more reactive. So here the answer of today's discussion is option C. By the way, many of you think no reaction. True. If you take only HF, no reaction. If you take only BF3, no reaction. But if you mix these two, then the reaction will happen. Remember this information. So this is the end of the discussion. I believe this video may be useful. Thanks for watching. See you in my next video. Bye-bye.